Hello, everybody. This is Shareq Nazir. I'm the assistant professor in the Division of Energy Processes at the Department of Chemical Engineering at KTH Royal Institute of Technology. Uh, Made a short presentation on the research that we do uh, in our group, and I've titled the presentation as Decarbonization, where we focus mainly on reducing the CO2 emissions, the capture of CO2 emissions, and also removing the greenhouse gases from air. The concentration of CO2 in the atmosphere has risen drastically from the industrial revolution times. It has crossed 400 ppm now, and it is a well-known fact that this rising concentration of CO2 is causing global warming. The IPCC, that is the Intergovernmental Panel on Climate Change, has uh, has told that uh, we should limit the CO2 emissions to the atmosphere as much as we can, and in a way that it limits the global temperature rise and it keeps the global temperature rise below 2 degrees by the end of the century. So our efforts are to decarbonize the energy systems in such a way that will limit emitting the CO2 to the atmosphere. Now, to understand decarbonization, it is good to understand the Kaya identity that speaks about different factors that that can help us decarbonize different technologies or can limit the amount of greenhouse gas emissions to the atmosphere. So the climate gas emissions are a factor of the emissions per energy use, the, the energy use per product that you're producing, that is the gross domestic product, GDP here, and then the gross domestic product per unit population, that is nothing but the amount of goods and products that a person uses, and then the population itself. Now, we mainly focus on the first two factors, which is climate gas emissions per energy use and energy use per GDP. So the first factor is nothing but the amount of emissions that you have per energy source. And so we focus more on replacing the fossil fuel sources with the renewable sources. Then the second factor is about energy use per GDP, speaks about the energy intensity basically. And in this, we are speaking about improving the efficiencies of the systems. When we speak about carbon capture now, it falls in the first factor where we are trying to emit less per energy use. Because if you have carbon capture and storage, then you're not emitting carbon dioxide to the atmosphere. And if all this fails, then we plan to remove the carbon dioxide from the atmosphere, and we'll come to that later. So the first project that I speak about here that we are working on in our group is about routes to produce transportation fuels from renewable feedstocks. And in this project, we are focusing on converting biomass into bio-oil and then using this bio-oil in the refinery to produce transportation fuels. Now, one of the critical steps is that this bio-oil that we produce is having a lot of oxygen, so we need to remove that oxygen. So we supply hydrogen to this step to hydrodeoxygenate this bio-oil. And in this project, we are focusing on getting this hydrogen in the best way possible. So whether it's through electrolysis, whether it's through natural gas reforming or biomass gasification, or through an integrated hydrogen generation process, hydrogen generation pyrolysis process. So this is one of the projects. Again, in this project, we are mainly focusing on replacing or using renewable feedstocks and also working with efficiencies of integrated systems. We work a lot with CO2 capture and utilization for utilization or storage. So what does CO2 capture means? It's you have a process, you have the fuel entering the process, getting combusted or getting converted, and then you have CO2 that is being emitted from the process. And that CO2 is captured either through post-combustion capture or pre-combustion or in oxy-fuel combustion manner. And then you transport that CO2 for either utilization or storage. In our group, we have been focusing in the last 6 months on process modeling and simulation of the chilled ammonia process. And we focus more on capture because capture accounts for 2/3 of the total costs of the full carbon capture and storage value chain. But then the shift now in our group is towards capture from industry, that is from refineries, cement, steel, fertilizers, and paper and bulk. The last part that I want to discuss is if you're not able to capture or reduce the emissions, then I think we'll have to end up removing the greenhouse gases from air. And so to be prepared for it, we have one more project that was funded by the Swedish Energy Agency, which deals with removing multiple greenhouse gases from air that is close to agriculture and farming fields. Now, when you speak on multiple greenhouse gases, we are speaking about CO2, CH4, and nitrous oxide. And we are speaking about agriculture and farming sector because the agriculture and farming sector accounts for the majority of methane and nitrous oxide emissions. Now, the direct air capture technology, which is more focused on removing CO2 from air, just focuses on CO2. And then it's a very costly technology. So to bring down the cost per ton of equivalent CO2 avoided, I think this concept would be a better fit because you're removing CH4 and nitrous oxide, which has got a very high global warming potential when compared to CO2. So removing methane and nitrous oxide will have a higher climate impact in addition to removing CO2. So this is the one of the projects that got recently funded in our group, and we focus on process modeling and simulation and techno-economic analysis here at KTH. Then we have policy frameworks. We are identifying policy framework for such a technology at Uppsala, and then we work on life cycle analysis, energy systems modeling at Swedish University of Agricultural Sciences. Well, this was a short introduction of the research that we are doing, that I'm doing right now. I thank you for listening to me. And if you have any further questions, you can contact me on my email address. And I hope you have a great day. Thank you.